Okay, so last time we just finished talking about the basics of dynamic burning of propellants and that it gets really complicated. You don't really see a dynamic burning due to detonations just because the detonations propagate so fast that any crossflow effects, things like that, normally don't affect a detonation, especially in the condensed phase. But since propellant deflagrations propagate many orders of magnitude slower, they can be influenced by just normal gas dynamic and flow and heat transfer processes in a way that detonations don't. and so they are highly susceptible to cross flows and things like that that influence erosive burning and dynamic burning and pressure changes and things like that. and so and you don't see anything analogous for detonations. And it's also because of real multidimensional effects like that that propellant combustion in real applications gets a little bit tricky. And the other aspect of dynamic burning that you need to be worried about is not only is it going to affect the performance of your gun system or your rocket motor or your propulsion system or whatever it is, it can also lead to instability. And so, as we learned earlier, propellants often respond to pressure perturbations by essentially overreacting. They're like your passive aggressive friend that if you ask them to do anything, they get all huffy and mad and sort of stomp away and then overreact. That's what propellants do. But then your friend will basically wind up doing it anyways. But the process of getting them to do that is it can be painful. So now for the propellant, we need to consider ourselves what conditions lead to instability, and that is runaway burning. And so if we're going to change, if we want to bump up the pressure, our most desired scenario is that the burning rate is that we change the pressure slow enough that the burning rate more or less follows is always in the steady burning regime, and the burning rate more or less follows the pressure curve, basically raised to some power. If it's and then if we can't do that, if for some reason we have to change it fast, then we would like it to do something like that. Maybe have a small bump, that small bump, that small bump can be designed for. What we don't want to happen is to have runaway burning, where the burning rate, because we change the pressure, is that it shoots to infinity, or it starts oscillating like this. We change the pressure, and so here is the pressure curve right here. And when we change the pressure, what we could wind up with, instead of this curve, which I have drawn right here, what we could wind up with is something that would look like this. And it just gets out of control. And it either winds up quenching the rocket or blowing it up, one of the two. And neither are desirable. And so how we analyze this scenario is, at least if you look at the propellant itself, Novozilov, a Russian scientist, this was published in the West in 1992. I don't know if he actually did the work in 1992. It might have been behind the. I never actually looked at his original paper, but there's a good chance it was behind the iron. It could have been behind the Iron Curtain for quite a while. But anyways, he did a linear stability analysis on the steady heat conduction equation and looked at its response to pressure perturbations. So for those of you who have had fluids too, it is just like the stability analysis that you'll learn there. I'm not going to go over that. It's a bit involved. As you know, stability theory gets to be a little bit crazy. But what popped out? But I will go over the results of it, but not the exact stability. Not the version of the Orr-Sommerfeld equation for this propellant. but I'll go over his stability criterion that he did that came out of this analysis. First, he defined a kappa, and kappa is defined as the difference between the surface temperature of the propellant and the initial temperature of the propellant times its temperature sensitivity. And then he defined gamma as just the change of surface temperature with respect to the change of initial propellant temperature held at constant pressure. Okay, so that's basically when he did his analysis and he non-dimensionalized it and all that good stuff and did the stability analysis. These were two parameters that basically popped out as being important. And he found that the burning of the propellant is stable if kappa is less than 1, and gamma can be anything. Okay. And if kappa is greater than 1, he found that the burning of the propellant is stable only if gamma is greater than gamma star. And gamma star is kappa minus 1 squared over kappa plus 1. Okay. And again, all these sort of popped out of his stability limits for his linear stability analysis. Okay, and so in terms of a map, it basically looks like this. We have kappa on the x-axis and gamma on the y-axis. And we are in this green region over here if we have stable burning. That means that if we poke the pressure or the burning rate of the propellant, eventually is that it might oscillate, but eventually those oscillations will die down and we'll have nice steady burning. And if we are under this curve here, which is actually defined by this, if kappa is greater than 1, then we are in an unstable burning regime, and the pressure perturbations grow without bound, and you wind up, and then basically bad things wind up happening to your propellant. Now, his stability analysis is for an isolated strand of propellant. You obviously don't want your rocket to operate in this regime, period. And so testing for things like this when they are proofing a new rocket propellant is one of the reasons it takes so long. And there's all sorts of safety measures and all sorts of stuff that they have to go through when they test a new propellant. At least to my knowledge, they are very hesitant to radically change propellant formulations. They are willing to mix they are very willing to mix different proofed and accepted propellants in different ways to get them to do interesting things. But in terms of a brand new ingredient actively used in a production type mode, that takes several decades at least. And so and basically part of the reasons is they have to do so many tests is that they have to experimentally map out these regimes so that they understand how it burns. They need to do all sorts of safety testing on it, and all sorts of other things, and just characterize it and then learn how to design with it. All that stuff takes time and it's very expensive. And so that's part of why especially the Army, they are very hesitant to mess with the propellants themselves, even though they do active research on looking for new propellants. But even if they find one that is viable and economical to make and all that fun stuff, it would be a very long time before it's actually used in a production mode. Maybe for a sort of niche type thing, it might be used before then, but in an active, very actively used, it takes a long time. Because again, they need to map out these effects. These are very nonlinear. And so, you need to find kappa and all that stuff. You need to characterize all of this stuff for your propellant, and then actually test it out. It takes forever. And again, there are all sorts of safety tests that they have to do, drop tests, electrostatic discharge tests, all kinds of things that are very standardized. So let me look at this. Okay, so now we're going to go over something called flame spread. And so what flame spread is you could consider, we considered the burning of a propellant down, but you could consider, you could have a very wide flat slab of propellant, and you could have a small little piece of it that is ignited in the middle. And you might be interested in basically how fast that flame sort of spreads out from that, spreads out along the surface. And then basically, because if you're interested in a rocket, you want that period where the first kernel ignites on the surface of the propellant, is you want it to engulf the entire surface as fast as possible. And so, and that process is called flame spread. And so basically it's just looking at flame propagation over an exposed surface. In your everyday life, there are examples of flame spread. If you've ever, watched a fire spread on a wall, I'm not insinuating that you guys are pyromaniacs, but if you've ever watched a fire spread on a piece of plywood or a wall, that process is flame spread, and it's analogous to the same phenomenon for a propellant. And both are very complicated. And so here, there's some experiments done at Los Alamos where they took a strand of PBX 9501, which is basically HMX with a bit of binder, and they have a small little slab of it. And they ignite it on this end here, and then they just watch how the flame basically moves across the surface. So when we were looking at the burning rate, we actually would have considered if this entire surface was engulfed in flame, how fast would it burn down? Now for the flame spreading, we are concerned with the velocity at which this flame spreads across the surface. And again, that has, and they're interested in that due to ignition of propellants and rockets and things like that. And so here, again, you definitely see edge effects where they basically cut the slab. But what they are interested mainly is in the piece in the middle that seems to propagate from right to left. And it's kind of jumpy, and in reality, it is really this is a pretty crude experiment. I think it was more or less just a class demonstration for us, if I remember correctly. They just had a little slab of it, and they just threw it on the table and just lit it on fire. It was nothing more fancy than that. Okay, and so this process is called flame spreading, and it occurs during transients in ignition. So as I said, as I showed with the movie, we have our flat slab of propellant, and most of it is non-burning. And here we have a small piece of it that has ignited. Could be due to a laser, could be due to a hot particle from an igniter. It could be due to a whole lot of things, but we'll just say we have this basically this small piece here that has ignited. Well, intuitively, this small ignition piece here is going to produce high temperature products. Those high temperature products are going to conduct heat to the nearby material on the surface, and then this flame is going to grow or spread. And that's exactly what is happening here. This flame is growing and spreading, and how fast and the speed at which this flame grows is called SF, and that is the spreading rate of the or the flame spreading velocity of the propellant. Okay, and then eventually, what will happen then is the flame will spread over the entire surface, and the entire surface will be burning, and then all the stuff that we talked about previously is now sort of in play. Okay. And so are there any questions as to the difference between the burning rate and the flame spreading rate, and even the sort of physical configuration for this flame spreading phenomenon? Okay, and Now, the flame spreading rate, as you can imagine, is dependent on orientation. If I have gravity oriented downwards, it will spread at a different rate, G. But if I have gravity oriented sideways, that will affect the flame spreading rate, or if it's pointing in the opposite direction. So gravitational forces also play a role in flame spread, and that's due to two things. One, you have that will affect the sort of direction, the direction that the plume of the combustion products move. If gravity is pointed down, they will move against gravity, just due to buoyancy forces, which will increase the how fast the flame spreads. If gravity is basically pointed up, then the combustion products move that way, and then that essentially retards the flame spreading rate. And then also, like I said, a lot of these propellants are sort of rubbery surfaces, and there will be a melt layer of propellant basically right before it burns, and that melt layer can flow, and then as it flows, it can also transfer heat. If gravity is pulling that melt layer into the cold condensed phase propellant, it will assist heat transfer. If gravity is trying to pull it away from the surface, it will basically hurt the heat transfer. And so flame spreading starts to become very situation specific. It starts to become very complicated because all of the really crazy fine details that are occurring at the surface start to matter. Okay, and it's important for rocket motor combustion, mainly because if you consider the entire process of a rocket from start to steady state burning, a good half of that is just due to flame spreading, just waiting for the flame to basically spread across the surface, and then after it spreads across the surface, then the combustion of the propellant is getting into a regime where the engineers sort of know how to deal with it. Okay, so now what can cause flame spreading, I just described some of the processes, is actually really complicated. It depends on whether the propellant is aluminized or I should say metallized with various particles. It's influenced by thermal radiation. You have convective heat transfer from the product gases potentially flowing over the surface. You have hot particles that can ignite and burn in the flame, but instead of just passively going up, they can sort of be shot up and then fall back down on the surface, and then that can cause the flame to jump. You have radiation from the flame and also other surfaces. You have conduction inside of the solid, basically, around from the bottom. And so this is a really, really complicated phenomenon. And also coincidentally, just as an interesting aside, this sort of phenomenon where you can have particles sort of jumping in front of the flame and landing on the propellant surface and sort of igniting another flame in front of the flame. That's also a significant reason why forest fires propagate so fast in, say, California, is that if you've ever had wood in a fireplace and you hear it crackle and it sort of will blow up, when it'll sort of blow up, it'll throw little sparks everywhere, and those sparks get caught up in the wind and all that stuff that is produced, and they eventually fall to the dry timber or to the dried brush in front of the flame and ignite another flame in front of it. And so oftentimes, if you look at forest fires, it's not just a nice smooth flame that's propagating, it'll jump around a bit. And that's part of why they're so hard to put out, is for things like that. And in the context of forest fire, those hot igniting particles are called firebrands. and so a lot of the same physics occurs in the flame spreading of propellants, forest fires, and and even unwanted house fires. Because instead of a propellant, this could be a piece of plywood or something like that. And so actually flame spreading has been studied in great detail in the context of fire safety. And so, and we're not going to discuss the fire safety applications to it, but a lot of the same physics applies, with the exception that the condensed phase is not energetic. That would be the main difference for us between the fire safety applications. Okay, and this was first analyzed by Mallard and Le Chatelier. They also did the first ever analysis of a gaseous deflagration wave. Depending on which theory is taught in the undergrad combustion theory or in the undergrad combustion class, this will be one of the theories that are often walked through when we're deriving the pressure dependence of a gas phase laminar flame. So here we're going to perform an analysis similar to what they did, and at its root, it's essentially the same thing that we did before, but instead of the flame moving down and we are going, and basically we are going down into the surface, we are now going tangential to the surface. And so this scaling a type of analysis gets to be extremely hand wavy, because they do consider control volumes that go across in the different sections of the flame. They do consider control volumes that go across both the gas and the propellant. And so by doing a control volume across the entire gas and propellant, they're essentially determining an averaged effect for both the gas and the propellant. And so there's a sort of averaging that is sort of done in their method. Okay, and so in this scenario here, we have our solid propellant here on the bottom in green. We have our flame spreading event, and after it ignites, it consumes the surface, and it produces a flame here. And the final combustion products after the flame zone are here at station 3. So this would be T3 over here, and it's of thickness some delta. At the ignition point, we have temperature T2, and then between T2 and T1, which T1 is the initial temperature, we have the preheat zone and the reaction zone. And so essentially what he does is he divides, basically much like a gas phase flame, he defines it into 3 different regions. One is a very cold region where basically nothing is happening yet. 2 is a preheat region where you have basically heat conduction from the products, heating up the unburned material, and then a chemical reaction zone where the chemical reactions actually take over. Okay, but again, instead of burning down into the propellant, it's burning along the propellant surface. And he's looking in the wave attached frame. So basically what's going on is he's feeding the gas and the propellant at the flame spreading rate. So basically this point here where it's igniting it is stationary in the mathematical from is basically held fixed. Okay, so again, this is again analogous to the burning rate analysis, except for it's now along the surface. And if you thought the assumptions we had to make for that analysis were hand wavy, this one gets even worse. But it does do a fair good job with the pressure dependence, which is really surprising. Okay, and so, and I'm not going to go through what they did in detail, but essentially what they did is they did an energy balance in this regime here, where they assume you have an enthalpy of basically of an average material going in through here at T1 and out through here at T2. And they assume this here is nothing more than basically cold reactants. And so they assume that there is no heat conduction going into this side of the control volume. But over here you have the flame. And so they assume you have heat conduction from the high temperature products going in. Okay, and so that's basically what they do in their analysis is they just balance the difference in the enthalpy going in and out with the heat conduction going in, and that's basically all their analysis is. Okay, and so if you do that energy balance, assume steady state operating conditions, et cetera, what you find, and assume constant specific heat, what you find is that basically you have m dot times Cp times delta T across the sides of the control volume. So this is just the change in enthalpy. And these brackets mean some sort of average, because remember, our control volume is now cutting across both solid and gas. And so we need to define what those averages are later on. Okay, and then that's equal to the amount of heat conduction going in. And they argue that that will scale with the final, with T3, which is the final combustion, or which is the temperature of the final products, with T2, which is the temperature at the ignition point of the flame, and then the thickness of the reaction layer. So basically, they're just saying is that the amount of heat conduction going in will basically scale with this thickness and this temperature difference and an average thermal conductivity. Okay, so are there any questions? Are there any questions? Any questions with that?
Professor, is that thermal conductivity? Are those, or I guess throughout different calculations, is that like a material property, or is that like, do you have to calculate that for every time you have to use something like this?
In a real case, if you're doing a real detailed analysis, this will be a function of temperature and the local mixture composition.
Okay, so you could calculate that lambda without having to go through this this equation first?
Well, here we're not calculating lambda. We're just basically estimating the amount of heat conduction going into the preheat zone of the flame. And so this here is actually just basically Fourier's law.
Okay.
Is basically what that is. And what's hand wavy here is and why I call this a scaling analysis is because we know darn well that the actual heat conduction going into the condensed phase propellant here, which is what we really want, is not going to be equal to just the simple temperature difference divided by a thickness of the reaction zone. It's going to be much more complicated than that. And so that's sort of why this is called a scaling analysis, in the sense is that we're just looking for an overall magnitude. But what he is saying, and what he is arguing, is that if you have a propellant where the reaction zone is going to be very thick, you should expect that the flame would spread, or you should expect that the heat flux going into the preheat zone of the flame along the surface would be significantly reduced by that. Okay, and that's all he's after here, is just a scaling analysis. Okay. Any other questions? Okay, so yeah, this is just the change of enthalpy, and this is the heat flux, or the conduction heat flux going in to the preheat zone. And again, these brackets mean some sort of averaged, and it's in some sort of averaged across the solid and the gas. Okay, and again, they're assuming that there's no heat conduction going through this plane right here, because again, it's nothing but cold reactants. Okay. Okay, and delta is the reaction zone thickness. And then what they say is that if you do another scaling analysis, you can say that the thickness of the reaction zone will scale with basically how fast you're feeding in the flame. So if you feed it in faster, then this zone will be thicker. Okay, and so that's our flame spreading rate. And then the faster the chemical reactions occur, the shorter you would expect it to be, which makes complete sense. And so you can do a very formal sort of scaling or non-dimensional analysis and come up with that same scaling. But basically this thickness here, delta, if the pyrolysis products of the propellant react instantly, you would expect this delta here to be extremely short. But if they take a long time to ignite and burn, then this delta will be extremely long. Okay, and so this scaling, and so this here is just a scaling analysis. For those of you who've taken convective heat transfer, I know when you're dealing with boundary layer theory, you do that quite a bit. And so you can basically come up with this scaling in a very similar sort of vein. Okay, so then we take the scaling here, substitute it into here, and then solve for the flame spreading rate. Okay, then what we wind up with is that the flame spreading rate squared scales. Notice I use a sort of squiggly equal sign. That means scales with. I'm not going to put an equal sign here just because this is by no means an exact enough analysis to where we can say it is equal to this. Okay, but at any rate, what we find here is that this flame spreading rate squared is proportional to the reaction rate divided by a mean density divided by a mean specific heat, and it is related to the amount of heat conduction going into the preheat zone. And if I went over the Maillard and the Chatelier version of a propellant deflagration, we would wind up with a functional form that is actually very similar. And it's almost, that is very similar for a gas and a propellant. So the leading coefficient is on the same order of magnitude as a usual or normal deflagration. Okay, and so you wouldn't, and again, we are assuming that all of those particles, all of those jumping effects, radiation, et cetera, none of those are applied to this analysis. This is purely heat conduction is the only thing that is heating up the cold reactants. Okay, and because it is dominated by heat conduction, as you can see by basically these two terms here, and actually this here is a thermal diffusivity, and so you can see that it is dominated by heat conduction, and so, and since both the deflagration rate or the burning rate and the flame spreading rate are both dominated by heat conduction, is that their speeds should not be too far off of from each other. Their pressure dependence and things like that are different, and I'll show that later. But their speeds should be close. Basically, if you experimentally measure one, and you should not find that the flame spreading rate will be 100 times faster than the burning rate of the propellant. Okay, so then we use our pressure dependence on the reaction rate, just like we did before, and we can find that the flame spreading rate of the propellant scales with pressure to the reaction order -1 over the mean density. Okay, and we just assume constant properties. Okay, with the exception of density, because that one we need to spend a little bit of time thinking about, because specific heat and all that stuff, you're not going to have much, if you're in the ideal gas limit, you're not going to have much of a pressure dependence with that. But there could be some pressure dependence that comes in with the density. So that one's going to take a bit of thought. And so what Maillard and the Chatelier did is they had no idea what to pick. So they picked the, the hell did I write here? Okay, they considered the two extreme limits. They assumed they just looked at the scaling law here for the flame spreading rate, and they looked at it based on, well, let's just look at one case where we examine the propellant density, and another case where we substitute in the gas phase density. Okay, and so as just two extreme limits, in reality, it will be somewhere between there. You know, but then they'll just look mathematically and see what that happens. And so what they found is that if you apply solid phase weighting, that is, you use the solid propellant density here, you'll find that the flame spreading rate scales with pressure to the reaction order -1/2. And actually, I'll be a little more explicit with that, like that. Okay, and so if the reaction is second order, which a lot of them tend to be, then you would expect that the flame spreading rate will scale, will basically scale to the square root, scale with the square root of the pressure. And recall that the burning rate scaled with pressure to the reaction order over 2. And so basically, if the reaction is second order, you would expect, if the reaction is second order, you would expect RB to scale with P to the 1. Okay, and so even the simple analysis shows that you expect different burning rate dependencies based on for the flame spreading and for the burning rate. Okay, and also it could be argued that you do expect this basically weighting the density based on the solid phase to be more accurate or more physical. And that's just because in many applications, the density of the solid is about 1,000 times higher than that of the gas. So if you are going to mass weight the densities, it's going to be skewed towards the solid anyways. Okay, but let's just play with the gas phase weighting, even though for physical reasons we don't expect that to be very accurate. And if you use that pressure to, or if you put in rho g here and use the pressure dependence of the gas phase density in the ideal gas limit, you'll find that the flame spreading rate will be P to the n-2/2, which then will scale actually just like the laminar flame speed for a gas. And so if you have a second order reaction, you would expect that the flame spreading rate for a propellant would not change. And that's if the density here is basically weighted for the gas phase. And so we expect it to be closer to this limit, but they didn't know what to do. So if you come up with a scaling analysis and there are two different extreme limits and you don't know, and you're not, and you're pretty sure of which one to pick, but you're not 100% sure, how do you go and make the final choice? And this is like about 100 years ago. So, or maybe not that long ago, but it was quite a long time ago. So what do? You go to the experiment, you go conduct an experiment, and you see what the experiment says. If the exponent on the pressure dependence is around 0.5, you know that as many of the hand wavy assumptions that you've made, you know that your your scaling analysis at least has the sort of first order effects sort of baked into them. Okay, so but what this analysis shows is that the flame spread should be on par or on the same order of magnitude as the burning rate. And you can conduct a much more detailed analysis by Foreman-Williams. If you stay in combustion, you're going to hear his name quite a lot, a bit like Zeldovich. And what he found is that the flame spreading rate scales with pressure to the 0.8 power. But then Siddiqui and Smith did an experiment where they burned a cylinder of double base propellant, where you remember before the question was asked, how do they keep the flame from basically going down the sides? And I said they use an inhibitor, and in Ken Ko's lab it was just nail polish, and that worked well. But what Siddiqui did is they did a very similar experiment, but they didn't do, but they did not apply that inhibitor to the side, and they just watched the flame go down the sides. Okay, and then how fast the flame went down the sides was basically was the flame spreading rate that they were after. Okay, and so that's basically how it worked. Is they just repeated they had a strand burner. They repeated the standard burning rate experiments, with the exception that they just simply didn't inhibit the sides. And then in their cameras, they basically paid careful attention to how fast the flame spread down the side. Okay, and then they chose a cylinder of double base propellant, because they're easy to prepare. And for a lot of these propellants, the melt layer the melt layer effects and things like that may not be that significant. Okay, and then they just watch the flame go down the side and then basically record how fast it was. Okay, and so these are some of their results, these aren't their results, but basically more modern experiments like that. Here's PBX 9501. That is HMX with a little bit of binder. And so here they have plotted both the deflagration rate of this. It's actually an explosive, but it can burn in a deflagration poorly in a deflagration mode. But so they have both the flame spreading rate and the burning rate of the propellant. And again, you can tell that at most pressures, except for at very low pressures, again, they're not too far off from each other. I mean, a factor of 3, 4, and for as crude as the scaling analysis is, that's actually pretty good. It's not 3 or 4 orders of magnitude, something like that. And furthermore, from the scaling analysis, we expected that the burning rate would have a steeper slope than the flame spreading rate, and that is actually what's borne out of the data, is that the burning rate of this energetic material has a higher pressure dependency than the flame spreading rate. And then furthermore, the flame spreading rate has an exponent of 0.5 of just about 0.54, which is basically very close to 2.5. Okay, and so basically, as crude as the theory of Mallard and Le Chatelier is, it does remarkably well at just predicting the overall pressure effects, and it neglects all of those other effects that I talked about. The melt layer effects, if there's any solid particles and things that can go and impact the surface in front of the flame, and all of those effects will basically speed it up. And none of that is included. And in part, these experiments are carefully chosen to basically use materials that basically minimize those effects, so that it's more consistent with the theory of Mallard and the Chatelier. But you can't just turn them off, so they're always there to some extent. And so the pressure dependence will not be exactly 0.5, but again, it does remarkably well. Okay, and so that's sort of what the sort of power of the scaling analysis can give you, is it can just tell you just a rough order of magnitude estimate of the important effects of a really complicated phenomenon. Okay, and also this is just a note. This is actually a page from my notes way back in the day, and the reason that the burning rate is lower than the flame spreading rate is just because for this we have a PBX 9501, which would actually be a composite propellant if it burns in a propellant mode, because you have a binder, which I'll draw in orange, and then embedded in that binder are a bunch of HMX crystals. Okay, and then essentially in the normal deflagration mode, this binder acts as a heat sink, and also its reaction is basically endothermic. And so it needs to propagate through an entire layer of that material before it can proceed to the next. Whereas the process is a little bit different for the flame spreading, is that it doesn't need to proceed layer by layer. And so essentially, the fact that the binder acts as a giant heat sink does not influence the flame spreading quite as much, just because it does not have to burn through the material layer by layer by layer. Okay, so are there any questions on this?
Just how much does the flame spreading affect the burn rate? So I'm guessing these were done separately, but in an actual event when you had flame spreading going on simultaneously with the burn rate, like does that affect it? And in some propellants, maybe?
Yeah, what it affects is the ignition transient. It affects that. And so that's,
guess there'd be more heat conducting into the burning propellant on the inside if you had the flame spread over it versus if you inhibited flame spreading in your sample.
yeah. So essentially why this is studied is in the rocket, if you're in a rocket, say if it's for a tactical missile or something like that, is you want the rocket to go from not ignited to full steady state operating conditions as fast as possible. But essentially just due to how the igniters work is that in the process from no ignition to steady state operation, there's always this flame spreading event that occurs. And so basically it's just part of the natural operation process of any rocket or gun system during its ignition transient. And the ignition transients are the most dangerous phase of these things. So they want to understand everything about them. Does that make sense?
Yeah, I think so. In a rocket motor, if you're igniting it from one end, you could have, a very large amount of ignition points at that one end and get rid of, I guess, this flame spreading phenomena, or maybe not get rid of it, but minimize how much spreading actually occurs by having a bunch of initiation points.
Yeah, well, that's what, yeah, if you've ever looked at I can talk about this because it's public knowledge. We studied the ignition process in the ignition train for for a NATO-based mortar system, not mortar, but mortar. Things the soldiers drop in tubes and they go flying out. And what ignites those is just a standard gun primer. And if you look at a gun primer, when you look at it at how it acts in a high-speed camera, is it doesn't produce much of a flame, but what it produces is a whole crap ton of really hot particles that go and basically impinge on various points of the surface of the material that you're trying to ignite. So for that type of system, what ignites the propellant are hundreds and thousands of hot burning little particles that just impinge on the surface and act as local heat sources. And then if you watch the flame spreading event, what will occur is you see all these little flame kernels basically growing and then merging. The other kind that you see, these are the ones used in the solid rocket boosters, or when they were using that that type of system. And in that system, what they used was a little rocket to ignite the big rocket, and that's just basically produced high pressure, high temperature combustion gases that then flowed over the entire surface of the propellant and ideally ignited its basically simultaneous. But there still was a flame spreading event with that too, because that's what that whole project was aimed for. Yeah, that project ended after I was in Ken's lab for basically 2 years, but I did a little bit of modeling on on that system too. But there is flame spreading for both, and NASA was very interested in that flame spreading event just so that they could in their design codes when they're designing propellants, so that they could actually have their codes account for this flame spreading event, because before we did that empirical correlation, it was a big question mark. They just had to assume something, but now they have actual data, and it helped them design something. Although I don't know what, they basically shut down the shuttle program, about 8-9 years after that, anyways. So I have no idea what they use it for now. But you are right, is that the designers will try to design the ignition system to make the flame spreading event as short as possible. Okay.
Yeah, thank you. And then
Yep.
for a gas, just a pure gas propellant, then do you worry less about the transient effects in initiation?
What do you mean by a pure? Oh, you mean
If you don't have a solid surface anymore for flame to spread, instead you are, a gas or.
They do worry about this to some extent. Like if you look at a gas turbine, and a gas turbine, you'll have a bunch of little fuel jets in a ring, and there are really interesting ignition transients with those, to where the spark will ignite one of them, and then basically the flame of that one jet will ignite nearby jets, and then it'll keep propagating around in circles. And so there is an interesting ignition transient with that, but as you said, that tends to occur so much faster than for a propellant, that in terms of a design, they normally don't worry about it too much. I mean, maybe nowadays, with the emission standards are getting so strict now, that they need to look at these really short-term events to reduce pollutants further, because there isn't much they can do about CO2 in the steady operating regime, but they need to look at these other effects where the combustion isn't 100% efficient yet. And so another one of those is the ignition transient, and this would be analogous to flame spread.
Yeah, that makes sense. Thank you.
Yep. Okay, and as I said before, orientation matters for flame spread of a propellant, because most of them, but not all of them, will form a melt layer right here. If you have the burning surface right here, you'll have molten sort of goo here, and that molten goo can basically flow down and then heat up that portion of the propellant. And so so that will also affect flame spread. And so fully understanding flame spread starts to become really, really situation specific. And so it's not studied quite as much, just because you need to get very applied before, because it's so situation specific. And then also surface roughness also matters. Okay, and that is presumably due to thermal radiation effects. Okay, and so basically, if you look at this flat slab, and I'll end the discussion right here, but if you look at the flat slab and you look at the flame spreading rate over a smooth surface, versus if you take a knife or something like that and make a bunch of cross hatches, and then basically rough up the surface, the flame will spread faster across the surface that is slightly roughened than the one that is not roughened, and that can only be due to thermal radiation. Basically, you have more of a surface here for thermal radiation to sort of impact and basically locally heat up a portion of the surface that basically has been roughened. Okay, and so for reasons like this, flame spreading becomes really difficult to simulate and basically model. And the only theories are for these really simplified flow configurations of just a perfectly flat slab with no melt layer, none of these particle effects, things like that. And so it gets complicated, but it's just part of the natural operating process of any system using a solid propellant. And so you just need to, hopefully it shouldn't be that big of a deal for the operation of your system, but it is just something to be aware of. And if you want precise, if you want to model it precisely and understand exactly how it works, this is another part of the ignition transient that you need to worry about too. Okay, so we are definitely out of time. So let's see.